you ever tried web development and thought, JavaScript is great, but I wish I could run other programming languages inside the browser with a similar performance? I have so much experience from using other languages that it's just harder now that I have to learn in-depth JS to code. Well, that's exactly what we will be talking about today. Hello everyone! Today we're diving deep into something that's changing how we build high-performance web applications, WebAssembly, otherwise known as Wasm. And in this video, we'll talk about how Wasm works, how you actually load and run it, and why developers are adopting it as fast as possible. Let's be honest, JavaScript is powerful, but it wasn't designed for everything we throw at it today. 3D rendering, game engines, video editing, scientific simulations, you name it. The web needed a way to run high-performance code without rewriting decades of existing C or C++ code bases. And that's where WebAssembly comes in. It's a portable compilation target, meaning you can take code written in languages and compile it into Wasm modules that run inside the browser's sandbox at blazing speeds. Note that Wasm is not meant to replace JavaScript, but rather designed to complement and run alongside it. WebAssembly is not a language you write directly. It's a low-level binary instruction format, though you can write it in text format as WAT. Think of it as simplified, safer assembly language for the web. It's designed to be fast to load, fast to compile, safe to run, and portable across browsers, operating systems, and hardware. WebAssembly defines two interchangeable representations of the same program, the text format and the binary format. The WebAssembly text format, or WAT, is a human-readable form designed for inspection and debugging by developers. It uses S-expression syntax, similar to Lisp, which mirrors the stack-based structure of the binary instructions. Since WAT is purely textual, it is not used for execution directly. Instead, tools such as the WebAssembly Binary Toolkit or WABIT convert it into a compact binary representation before deployment. On the other hand, the Wasm binary format is the canonical executable encoding. It is designed for fast decoding, deterministic layout, and compact size. A fixed opcode represents each instruction and data type. Because of this structure, decoding speed can reach hundreds of megabytes per second, making it suitable for streaming compilation. Binary modules are platform and endian independent, ensuring deterministic behavior across browsers and architectures. You can also achieve that binary format through conversion from other programming languages. Here we will show you how that works. Let's start by writing your code in a specific language. It may be C, C++, Rust, Python, whatever you prefer. The toolchain will then compile that code into a Wasm binary formatted module. This way, JavaScript can now read your code, and your JS code can now load that module. The Wasm module exposes functions that JavaScript can call, and vice versa. Now you can freely use those functions in your JS code.
Let's start with a very simple example. Imagine you've called a function like this into a file and called it add.wat that adds two integers represented as a and b, then returns their sum. Here, we declare a function using the keyword func, followed by the function name add, and it takes two 32-bit integers represented by a and b. Note that the function name and variable names have a $sign preceding them, and we are also declaring the result to be a 32-bit integer. The body of the function includes a code section that details what is done to get the result. Here we push the parameters a and b onto the stack, and the function i32.add pops the two variables and pushes their sum. The last line here is an export section, making the function callable from outside the module. Using this example, we can convert this WAT file into a Wasm file using the wat to Wasm command from the WABT based on the following format. -o add Wasm. And we can view it like this, and you can see that it is in binary, but it's reformatted into hexadecimal, so it's a smaller format. And in a separate file, we can create an HTML and JavaScript loader just like this. And in this example, the function WebAssembly.instantiate compiles and runs the file. The function is commonly used when run with the browser, and this also shows how JavaScript works with WebAssembly by incorporating it into the code rather than replacing it entirely. When we host it locally, it will look like this. There, the output is 5 plus 8 equals 13.
Originally, WebAssembly was designed without native support for threads or shared memory to maintain a simple, deterministic execution model. However, as performance requirements grew, the WebAssembly threads proposal was introduced. This extension enables multi-threading using shared array buffer and atomic instructions, closely mirroring the low-level concurrency features of native environments. Despite these advancements, WebAssembly's concurrency is still more limited than that of native environments. It lacks direct access to OS-level threading APIs and system resources. Moreover, communication between WebAssembly modules and JavaScript remains subject to serialization, memory copy overheads, and data processed the WebAssembly JavaScript boundary. Now, this is where WebAssembly becomes really interesting for developers. With its linear memory, Wasm operates on a single continuous memory buffer. If you've used C pointers, this will feel familiar, but this time it's safer and sandboxed. Browsers can also compile Wasm while it downloads. This means big modules start running almost instantly. Unlike JavaScript, Wasm skips the just-in-time or JIT code generation. Now we can experience minimal garbage collection and unpredictable pauses. Wasm is language agnostic, since anything that compiles to Wasm can run in the same app. You can mix Rust modules, C++ modules, and still have a JavaScript user interface. So where does WebAssembly actually shine? Wasm can be used to create game engines, video editing tools, CAD and engineering simulations, image processing and AI filters, high-performance cryptography, running other languages in the browser, and edge computing through WASI. If your app needs heavy computation, Wasm is practically built for you. Even though Wasm is powerful, it's not magic. Here are the real limitations. Passing data between JavaScript and Wasm is overhead, especially in large arrays. Wasm can't access the DOM directly. It still needs JavaScript as its middleman. Multi-threading depends on shared array buffer, which requires cross-origin isolation. Tooling is improving but can be intimidating, especially compiling C or C++ to Wasm for the first time. None of these are deal breakers, but they're worth keeping in mind. The future of WebAssembly is incredibly exciting. WASI will let Wasm run on servers, on the edge, even as portable CLI tools. The component model aims to make Wasm modules plug and play across languages. We're moving toward a world where you compile code once and run it anywhere. Browser, server, desktop, Internet of Things. WebAssembly started as a browser technology, but is quickly becoming a universal execution format. And that's WebAssembly. If you want a more detailed discussion of Wasm, check out the Medium article found in the description. Thanks for watching.